Hello again. It's Saturday morning in Columbus, Ohio, and Vinny the cat and I are here to present to you another video lecture. This is video lecture 11.1. We are starting chapter 11. The title of chapter 11 is Rolling, Torque, and Angular Momentum. So we're still talking about a lot of the same ideas from chapter 10. Chapter 10 was about the rotation of a rigid body about a fixed axis of rotation. And in chapter 11, we're really just going to relax the fact that the axis of rotation no longer needs to be fixed. We're going to let the axis of rotation for a rigid body move. And the first topic of chapter 11, rolling, is, as cliche as it sounds, as basic as the first real technological invention of humanity, the wheel. Turns out there's a lot of good physics in understanding how a wheel rolls along a surface. And that's what we're going to start chapter 11 studying. So if you want to read more detail, chapter 11, section 1 is entitled Rolling as Translation and Rotation Combined. And I'm going to show you an animation of those two things, translational motion, rotational motion, and then when you combine them to get rolling. Hopefully the pictures will help you understand exactly what we mean by those words. But the key idea is what I just said. Rolling will be thought of as translation combined with rotation, and we're no longer going to require that the axis of rotation be fixed. So let me go ahead and get started by showing you animations / pictures. I think visualizations help here a lot. So let me go over to a picture here on Wiley+. And we have a rigid body that's just going to roll along a horizontal surface. It can't be an icy smooth surface. Turns out you need to have some friction in general. But I'm not going to worry about that quite yet. Let's just say we've got something that can roll. The animation says that it's a sphere in this case, although when you look at that, it could also be a disc, a cylinder. So it's something that can roll, such as perhaps a sphere. And it's going to roll to the right, and we've marked 3 points on it. The very center point is marked with a black X. There's a point out on the rim that's been painted with a red dot. We're going to follow it as the object rolls. And then there's another point halfway out the radius between the center and the rim that's been painted with a blue dot. So I'm going to run the animation. The object's going to roll to the right. And we are going to look at the motion of those 3 special points. Okay, the 3 special points, the black point, the blue point, and the red point. Let me bring the time slider back a little bit. Maybe to there. Okay, now you probably were thinking, and you would be correct, that the black point in the center is that special point called the center of mass. And notice that the trajectory of the center of mass, which is the black trace here, that is just straight line. That's the simplest trajectory there is here, isn't it? Once again, the center of mass motion is the simplest to deal with. And it turns out that that center of mass moves with a certain velocity that we're going to label VCOM with an arrow on top. And as this thing rolls, this perfectly rigid body, the VCOM is constant on this horizontal surface. Then there's the blue point, halfway between the center and the rim. Look at its trajectory, its trace, that blue curve. Pretty complicated. Certainly not a straight line. Now look at the red dot that was on the rim of the object that rolls. And look at its trajectory. Also not just a simple straight line. Pretty complicated. And perhaps the more interesting of the two, the blue and the red. That red trace shows very clearly that when that particular point, the red dot on the object, sphere or disk, whatever it is, is in contact with the ground or floor, right about there, that trajectory makes a very sharp point called a cusp. That's a clue about the velocity of that red point at that moment when it's touching the ground. Have a prediction what the velocity is? We are observing this thing, by the way, standing at rest on the ground. We are not riding on that thing. That's important. We are at rest on the ground, watching this object roll by. But that sharp cusp in the trajectory is a clue as to what the velocity of that red point is at that moment right there when it's touching the floor or ground. And by the way, that red trajectory of that point on the rim of the wheel is very famous. It's called a cycloid. And if you want to know more about the mathematical shape of that curve and other physical situations where that curve is important, take Physics 310, Classical Mechanics. All right, so there I'm just showing you the rolling motion. I'm showing you that the center of mass motion is the simplest, and that a point on the rim moves in a very special way called a cycloid. And there's a clue as to what that point's velocity is on the rim when it's touching the floor. All right, now I want to go to a different picture. Again, though, I'm going to show a sphere or a disc or a cylinder, some rigid body that's going to roll to the right without any slipping of the point of contact with the floor. And I've also labeled X and Y axes with units and everything. And you can't see it here, but I've got a little slider up above that's labeled theta in radians. And that's going to let me control the angle that we roll the object through. Right now it's at 0, and its center is lined up with the y-axis. I'm going to roll it through about what we would call a quarter of a complete revolution. Right about there. Okay? The theta slider up above says 1.57 radians. And if you remember your friend pi, that's pi over 2. So we have turned the object through an angle theta of pi over 2 radians. Now, while that has happened, I'm going to be moving it back and forth. We've done a couple of things in this animation. We're assuming it's a uniform disk or sphere, okay, so that the center of mass is at its geometric center. And when I slide this thing forward about a quarter of a revolution, it shows with a black arrow labeled XCOM how far the center of mass has moved. You can see that it has moved to right above that point P. Okay? Straight out along the X direction. At the same time, I've painted a red curve along both the floor and that part of the disc that has been in contact with the floor. It's painted red. And that turns out to be an arc length. I'll call it S. And it's that arc length along the disc that has been in contact with the floor during this rolling. And the key thing to note is that that length of that red stripe along the ground, which is the same as the red curve along the arc, along the periphery, S, is equal to the XCOM, how far the center of mass moved to the right. And that's shown right up above with the formula XCOM equals S. The whole point of this animation is to show you that XCOM, just the horizontal distance that the center of mass has moved, and S, the arc length through which the disk has rolled, are equal, no matter where I put the thing. XCOM equals S. But there's a formula for arc length S. It's the radius of the thing times the angle it's turned through. So XCOM equals radius times angle, just from that basic picture. And then, thinking ahead a little bit, if you take the time derivative of both sides, XCOM becomes, but this is only for magnitudes, VCOM, magnitude. If you like, the speed of the center of mass. And r times theta, when you take a time derivative, becomes r times the absolute value of omega, The absolute value of the angular velocity, r is constant. The absolute value of angular velocity is angular speed. So an equivalent restriction for rolling without slipping is that VCOM equals r omega for magnitudes. We're going to use that formula a lot. We could even take another derivative of the VCOM equals r omega. And the VCOM becomes ACOM, magnitude, acceleration of center of mass. And the r omega becomes r times alpha, magnitude, magnitude of angular acceleration. We'll use that one too. Okay, now I want to show you one more. But before I do, let me go back to my notes and let me point something out. What we're going to note is, first of all, I'm going to highlight it down here so you can see it. One of the key results we now have is that an object that's rolling along without any slipping has this constraint between the speed of the center of mass and the angular speed of it. The speed of the center of mass, VCOM, magnitude, equals omega, magnitude, times the radius. For a disk or a sphere, anything that can roll, that's just rolling along a surface. Now, here's the next thing. It's going to be very important for this kind of rolling type motion. The motion of a rigid body through three-dimensional space, that's what we have now, can be analyzed as two separate motions combined. Two separate motions combined. That might feel like we're making things more complicated than we need to. Now we've got to do with two motions. But the kind of rolling type motion or anything where an object's moving through three-dimensional space, that's translation, while also rotating, can get very complicated to deal with. And about the only way you really can make any headway analyzing it is if you break down that complicated actual motion that you observe in 3D into two separate motions. And Newton then will help you analyze each of those two separate motions. And here are the two separate motions. What we call translational motion of the center of mass, COM. Just how does the special point called the center of mass move through space? And for that we use Newton's second law for the motion of the center of mass. ACOM arrow equals F net external arrow over M. The net external force acting on the object divided by its total mass. But note it's a vector equation. Vectors on both sides. So you have to work with components. And that's how you do deal with the translational motion. You find the translational motion of that special point called the center of mass. You combine that knowledge with the rotational motion about an axis through the center of mass. Okay? You look at translational motion of the center of mass through space, and then combine that with rotational motion about an axis through the center of mass. For that, you need Newton's second law for rotational motion, which we learned in Chapter 10. Angular acceleration equals the net external torque, but it's got to be calculated about an axis through the center of mass, divided by the rotational inertia for an axis through the center of mass. And those are the two key physics ideas we will use to analyze rolling. Two separate Newton's second law problems. Translational motion of the center of mass, rotational motion for an axis through the center of mass. Now, by the way, if you're wondering how we can get away with taking an object that may be moving around very complicated way through three-dimensional space and break it down into these two separate Newton's second law problems, that's a legitimate thing to at least question. Why are we allowed to do that? Well, it turns out you can prove that you can break down the motion into these two parts. It's called Chasles' theorem. Just want to let you know that you can prove that it's okay to do this. And that would be a more advanced mechanics course. Okay? All right, so now what I want to do is show you one more animation that shows you exactly how we're going to think of the rolling of a disc slash wheel or sphere, like a bowling ball, the rolling motion of an object as translational motion of the center of mass and rotational motion about an axis through the center of mass. How does that come out for something rolling along a surface? All right, let me show you now. Oh, I have to. Bear with me. Okay. Now, 3 pictures here. Think of them as 3 spheres or 3 discs. Top, middle, and bottom. And I'm going to drag the time. There's a time slider up at the top that you can't see. I'm going to drag it and let time tick away. And the 3 things that you see are going to move in a certain way. The top picture is going to be pure translation. That disc, that rigid disc, is going to just be dragged to the right. And every single point on it's going to have the same velocity. And that's what pure translation means. So first, when I drag the time slider, I just want you to look at the top figure, where we have what's called pure translation. You see, it's just like we're dragging the thing to the right. And every single piece of the disc on the top has the same velocity. That's what we mean by pure translation. And if I hover over the red arrows, there are 5 of them at 5 different points on the disc or sphere. How about the one in the middle? That should be the center of mass. And up pops the little arrow, VCOM. Sure enough, that's the velocity of the center of mass. It's to the right. But because this is pure translation and every point on the rigid body has the same velocity, then every point has that same V. So the point out here in the front also has a velocity VCOM, but the point at the top, VCOM, or the point at the bottom, VCOM, or the point at the left, VCOM. That's pure translation. All right, let me bring the time slider back. Now I want you to focus on the middle rigid body. It's going to undergo what we call pure rotation about an axis through the center of mass. This would be an example of what we studied all throughout Chapter 10. The object will rotate about an axis, and that axis won't move. The axis itself won't move. And in this case, for this chapter, the axis will be through the center of mass. So now I want you to look at the middle object as I pull the time slider. Pure rotation about the center of mass, about an axis through the center of mass. Okay, let me stop it about there. Note then that there is no velocity vector at the center of mass point. It has no velocity. But the 4 red dots on the rim, those have velocities because those points at this time are rotating. A point at the top has a velocity to the right. I've labeled it there V-tan. It's the tangential velocity. Well, it's to the right. The point on the front also has a tangential velocity. That's down. The point at the bottom has a tangential velocity to the left. The point on the left has a tangential velocity up. Now, all those tangential velocities have the same magnitude, but they have different directions. But we know from Chapter 10 what those magnitudes, V tangential magnitude, what that is. Chapter 10, Section 3, combining linear kinematics and rotational kinematics. For a rigid body rotating about an axis, the magnitude of the linear velocity of a particular point equals the radius of that point, distance from the axis, times the magnitude of the angular velocity. In shortcut language, V tangential equals R omega. So every one of these V tangential arrows has a magnitude that we would say is equal to R times omega, where omega magnitude is the angular speed at which that thing is rotating. That's the middle picture, pure rotation. Now the bottom picture is what you get when you combine, and by combine I mean add. Combine together the pure translation in the first picture and the pure rotation in the middle picture. And that's going to give you rolling. So now what I'd like you to do is focus your eyes on the bottom picture as I run the time slider. The bottom picture, where I think that should look to you like something that's rolling along a surface, the bottom picture. Rolling, we say rolling without slipping. Let me bring it back to about there, where one of those points on the rim is touching the floor. Okay? All right, now I want to focus on that picture. And I want to understand the velocity vectors that are all there present in the bottom picture, because they're all those red arrows are velocities. And I want to understand them. And I contend that to get those red velocity vectors in the bottom picture, we're going to take the red velocity vectors in the top picture, pure translation, and add to them, vector addition, the red velocity vectors in the middle picture, pure rotation. Because we're going to combine translation and rotation to get rolling. Let's start with the middle, the center of mass, because that's the simplest. Okay? So, look here in the middle, the center of mass point. Now that red arrow is labeled V net, the net velocity of the rolling object. That's going to be the velocity of that same point in the top picture from translation, VCOM, plus the velocity of that same point in the middle picture from the rotation, that's 0. And so I just get that the V net for the center of mass is VCOM. And you can see that the red arrow for the center in the rolling picture is the same as the red arrow for the center in the translation picture. All right, that one's an easy one. Now let's look at the point on the top part of the rolling object, up here. Look at that V net. That's a long arrow. That means that point at the top of that rolling object is moving very fast. How fast exactly? That's an interesting question. Well, it must be the vector addition of VCOM for the top point in the translation plus V tangential for the top point in the rotation. It's the sum of those two vectors. Well, that explains why it's very long up there in V net. But exactly how long? Well, we'll see in just a second. Now let's look at the point on the bottom point on the rolling object, the point that is, at the moment, in contact with the floor. Now I contend at that point that's at that moment that's in contact with the floor, and we're standing on the ground watching it roll by, to us has a velocity of 0. That's why we were getting in that cycloid trajectory, that sharp cusp, when the point on the rim of the object touched the floor. Because, as we watch it on the ground, at the moment it touches the floor, its velocity is 0. And here's how we get that. We take the velocity in the top picture for that point touching the floor, VCOM for translation, and we add to it the velocity V tangential in the rotation. But notice the V tan at that bottom point is to the left, and the VCOM of the bottom point is to the right. So when I add those two vectors, they're going to want to try to cancel each other. And in fact, they must exactly cancel each other so that I have no velocity vector at all for V net in the bottom picture. But if those two velocities, VCOM to the right and V tangential to the left, are going to cancel each other, they must have equal magnitudes. But the V tangential magnitude is R omega. So it must be that the VCOM magnitude and the R omega must be equal, which is what I just said a little while ago. For rolling without slipping, the magnitude of VCOM equals R times the magnitude of omega. And that's yet another way to see that. That's how you get that the velocity of the point that's touching the floor is 0 for an object that's rolling without slipping. Note, it's a whole different story if that rolling thing is slipping across the floor. Think about bowling. How many of you have been bowling? Now, you can get the ball to roll without slipping down the floor, but depending upon how you throw it, you can get other things. You can get it to spin as it goes down the floor. That's not what I'm talking about now. Or you can get it to skid as it rolls down the floor. That's not what I'm talking about now. I'm talking about rolling without slipping. That means the point at any given instant that is touching the floor has a velocity of 0. And to get that to happen, the magnitude of VCOM must equal r times the magnitude of omega. And I keep saying that because it is so important to understand that point. All right, so now I'm going back to our slides. And I will highlight yet again this relationship. Magnitude VCOM equals magnitude omega times r. I have a couple more pictures to show you here. First, I have a photograph that the author of your book took of one of those bicycle wheels that's been removed from the bicycle, and it was just made to roll along a tabletop, and took a photograph of it. And it might be hard to see here, but if you look very, very carefully in the photograph for the duration of the exposure, the top part of the wheel, say this point right here, to us as observers on the ground, is moving to the right with a very large velocity, whereas the point down here on the bottom has a velocity of 0. And the way we know that from the photograph is by looking at the spokes on the bicycle wheel. In the exposure of the photograph, the spokes pointing downward towards the floor are sharp, in focus, not moving very fast when we took the photograph. But the spokes going up towards the top are blurry because they were moving fast for the duration of the exposure. That's just a photographic evidence that the point at the top of a rolling wheel is moving faster than a point at the bottom. The other two pictures are showing you V equals R omega, but with a little subtlety. First, this picture right here. Now in that picture you have a sphere that's rolling towards you. So the VCOM is coming straight out of the screen towards you. And it's drawn a sideways dash line through the center of mass and another dash line through the floor. And the distance from the line through the center of mass and the line through the point of contact with the floor is the radius, r. And the formula then is VCOM equals omega r. No problem. Every once in a while, books like to trip you up by letting the thing roll through a kind of a, I don't know, a trench or a grooved track, so that the point at the very bottom of the sphere, down there, is not actually touching the surface. Instead, it's touching at these 2 points here. If you ever come across a situation like that, what's the no slipping, the rolling without slipping condition? It's that one right there. VCOM equals omega, and then I've used little r. What's little r? Well, I drew a dash line through the center of mass, and then another dash line that goes through the point of contacts, the points of contact. And then r is the distance between those two, the little r, notice, not the big R. You can see what the little r is right there. Not staying for some reason. Yeah, it's not staying there. Can't see it. In case you ever get a problem with an object rolling through a grooved trench. Okay, now let's start applying those ideas, okay? Let's start applying them. All right. This is now Chapter 11, Section 2, in which your author talks about forces and kinetic energy of rolling. I'm going to start with kinetic energy. And I'm just going to state a result that we're going to use a lot for the rest of this chapter. So let's say you've got an object that's rolling along a surface, not slipping as it goes. It's moving, so we can ask how much kinetic energy does it have? What is the kinetic energy of an object that rolls without slipping? That's the question. And the way you answer it, I'm just going to tell you the result. You calculate the kinetic energy for an object that's rolling without slipping by breaking up the rolling into 2 parts. Translational motion of the center of mass and rotational motion for an axis through the center of mass. So kinetic energy for pure translation plus kinetic energy for pure rotation about an axis through the center of mass. You just two parts, and you add up the kinetic energy for each part. And so I'm going to tell you now all you got to do. For K translation, you just use our old friend 1/2 mass times v squared. But this would be the total mass. And technically, it would be the magnitude of the velocity of the center of mass squared. There's Vinny saying good morning. That's K translation. Now for K rotation, for an object through the center of mass, you use the formula we were introduced to in chapter 10 for pure rotation about an axis. 1/2 times the rotational inertia, but it must be for an axis through the center of mass, times the magnitude of the angular velocity squared. So 1/2 mv/com squared and 1/2 I/com omega squared. And when you add those two together, you get this formula right over here. Okay? K rolling. Notice how I've labeled it. It's the kinetic energy of rolling. 1/2 mv/com squared plus 1/2 I/com omega squared. Then just remember one more thing that's going to be true for an object that's rolling without slipping, and we will use it a lot. The magnitude of v/com equals the magnitude of omega times the radius, where that's all about magnitudes. We have that has to be true as well. That means the v/com here and the omega here are not independent of each other. They must satisfy that relationship, and we will use that as we solve problems. Okay, so just remember, if we've got a rolling object, that's the formula you use for its total kinetic energy. All right, now I'm going to stop this video, and then I'm going to have a part 2 where we look at forces involved for an object that's rolling. But that's all for this first video.